In this final exercise, we look at a method of proof. Now, you may be wondering why we're looking at this method in the context of the exercises and chapters we've just looked at, and really the only connection is to remember in sequences we talked about the recursive term or recursive concept, where you can express a term by referring to the term before it or the term after it. In this method, while we don't look at individual terms, we're going to use the concept of recursiveness and as a means by which we can prove something. So we're going to prove a statement for, say, k terms, and we'll show that a statement is true for, say, k terms, and then prove it true for k plus 1 terms. So k can be any number, and you could probably reason for yourself that if you could show that some statement was true for 10 terms, 10 items, and prove that it was then equal for the 11th item, you would start to wonder, well, what if I started with the 11th item? Would it be true for the 12th item? And in most of these cases, yes, it will be, but we wouldn't be asked to prove. But the process of mathematical induction is using that very concept. Now, like I said before, while we won't be using a specific number like 10 or 11, we'll be calling it k, and then we'll be proving for k plus 1. That then enables us to apply any value to k, and if it works for k and you can show it works for k plus 1, then you can assume or say it is true for all k. The good thing about proof by mathematical induction is you only use this proof when instructed. It appears in every Extension 1 exam, and it'll be no different for you. In the HSC, there will be a question about mathematical induction. You could pick up any past HSC exam at the moment and go looking through, you'll find a question on mathematical induction. So it is a really, really important exercise and concept to master, because this is one you know is going to appear in the HSC. And it is like it's saying here, it's a particular type of proof which is a real example of thinking logically. Like I've been saying, if you can show it's true, an expression is true for k terms, then and prove it's true for k plus 1 by our sense of logic, it must work in all cases. So, as it says right here, because this is a method of proof, it's mostly about and in proof, you're given the statement, in this case, you'll be told whether it's true and what it's true for. So you'll be able to set up your statement based on the information you're given. What then becomes the focus is this process of logical thinking. Now, it's pretty straightforward in that the process has 4 steps. So they're shown here, and it must be really obvious in your answer that you're addressing 4 aspects to the proof. You could start off step 1. If you just glance at this, you can see, yep, step 1, step 2, step 3, step 4. If a marker sees something presented in that format, they're going to know that you've got the process down pat. 4 steps. So the first thing you master is getting the presentation correct. So once you know that you're basically having 4 main paragraphs in your solution, what goes in them? Well, step 1 is the same all the time. You will start with these exact words. Show the statement is true for n equals 1. Now, what comes after that depends on the nature of the question or the nature of the statement. Let me just scroll back up here. So an example would be to prove by mathematical deduction for all integers n that are greater than 1, integers, whole numbers, that 1 cubed plus 2 cubed plus 3 cubed plus blah 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 up to n could be replaced with 1/4 n squared n plus 1 all squared. Where did this come from? It doesn't matter. We don't have to know it. We will be given this. What we have to be able to do is show that this statement is true, like you've heard me say, maybe for up to k, and then prove it true when we've got k plus 1. So, back to here, step 1, we're always going to start, show the statement is true for n equals 1. And basically, you will be showing that the left-hand side of the statement, when n is 1, is equal to the right-hand side of the statement when n is 1. So back here, we would just have when n is equal to 1, left-hand side equals 1 cubed. Right-hand side equals 1/4 of 1 times 2 squared, is that right? Which is 4, and 1/4 of 4 is 1, which was the left-hand side. Therefore, we can conclude the statement is true for n is equal to 1. Now, that's always going to be the easy step. Step 1 is the easy step. But step 2 is equally as easy. We're going to suppose, and again, you can use this bolded wording, suppose the statement is true for n equals k, a positive integer. You notice back here I said, please learn these off by heart. These are statements you can learn off by heart and put them in your working, and know that you're on the way, just by learning a couple of statements off by heart, you're on your way to convincing a marker that you know how to prove by mathematical induction. What we do here in step 2 is we introduce k into the statements. So this, it goes on to say this means substituting n equal to k, which involves rewriting the statement using a k. So while you're not writing out this sentence that I've just read, you're actually doing it. So up here you would have 1 cubed plus 2 cubed plus 3 cubed plus k cubed equals 1/4 k squared bracket k plus 1 squared. Now, that seems all pretty easy. Mathematically, we've not come to anything challenging so far. Step 3 Now remember I said this whole process is based on the recursive idea. So we've supposed the statement's true for n is equal to k. We need to prove the statement is true for n equals k plus 1. And again, I should have bolded that first sentence, because that could be how you start your third paragraph. Now prove the statement is true for n equals k plus 1. This is the only part that becomes mathematically challenging. The only mathematical bit is really in here. I won't go into too much detail about how you do that, because it changes from question to question. For every different statement that's given, and you're going to see lots of different statements. In fact, you're going to see 3 different families of statements. For each different one, you approach it in slightly a different way, and I'll come to that and talk about that. But basically, you need to sub k plus 1 into your statement, and then show the left-hand side is equal to the right-hand side. Once you've done that, which I'm not dismissing because it can be mathematically challenging, step 4, you can then conclude that the statement is true for all positive integers. And that's it. So that is the process. Outlined for proving by mathematical